No. Here you go. You can put that on somewhere.
Okay. How's that?
Tap it. Make sure it's.
Is it good? Oh, I can't hear
I'm
it.
gonna turn it up a little.
Oh, cool. Yeah, is that? Can you hear me? Should I move it up? Maybe I'll move it up. We're good?
Centrally, but it may be okay.
Is that cool? Yeah? You can hear? I can't really hear, but I'll let them tell me. Maybe I should just, yeah. There we go. How's that? Better?
So I'm gonna.
Yeah, let's go.
All right. All right, good morning. Let's do this. So we're glad to have another lecture series from Cliff Cheung of the California Institute of Technology, who's going to tell us about scattering amplitudes and symmetry. We have to add "and symmetry" to the name of every talk at this school. So scattering amplitudes and symmetry. Cliff.
Cool. Okay, so before I start, first let me thank the organizers for putting together what really looks like an extraordinary TASI summer school this year. It's really impressive, so kudos on that. And also thank you for inviting me to speak here this week on a topic that's kind of close and dear to my heart, which is scattering amplitudes. So yeah, so that all said, I have to confess that when I first sat down to start preparing my lectures, I encountered kind of a conundrum, which stemmed from the fact that I already lectured on scattering amplitudes at TASI in 2016, roughly 7 years ago. So I was thinking about my options. So option one is I could just do it all again, exactly the same, verbatim, no changes, maybe with a little more excitement, panache, and better special effects. But in Hollywood, that's called a reboot. And I think nobody likes reboots, right? No one wants to see that. So instead, I'm going to do the sequel, okay? What happens in the sequel? So in the sequel, we have kind of the same basic elements, characters, world. But once everyone's up to speed on the last movie, we kind of move on to maybe more interesting pastures, a storyline that's different than last time, and hopefully more interesting. Now, I think I can do that because, as it turns out, scattering amplitudes as a field has actually changed a fair amount since I last spoke about it here. In fact, looking back at my old notes, I'm kind of weirdly gratified because there's whole passages that are just completely obsolete. They remark on things like, wouldn't it be amazing if we could apply, this and that scattering amplitudes technique to this other problem of import in some other field? Wouldn't it be amazing if we could understand this mysterious structure, which I'll tell you about in scattering, with some first principles understanding? Those kind of like fill in the blanks got filled in, and I think when those kind of developments appear, I'll try to highlight those more recent advances in my lectures. Now, if you actually ever go to a scattering amplitudes conference, you'll notice it's a really kind of broad spectrum of people from many different backgrounds. So there's particle physicists, which is what I would describe myself as, string theorists, and collider physicists, phenomenologists. More recently, even pure mathematicians, cosmologists, and gravitational wave physicists, all interested in scattering for very different reasons. Okay, so right at the top here, I wanted to convey some of my excitement, but also my own personal selfish reasons for why I care about scattering at all. Like, why are we caring about this kind of last chapter and sub-chapter in your QFT textbook? And it boils down to a very basic question, which I want to start here with, which you've kind of grappled with, I think, in the last couple weeks. A basic question, which is what defines a theory? What actually defines a theory? Okay, so there's many good answers to this question. Maybe it's equations of motion if you're a classical physicist. Maybe it's a Hilbert space and Hamiltonian, or maybe it's an action principle and a path integral. Okay, these are all fine answers, but let's unpack that slightly. Okay, so what did I say? Well, maybe it's defined by an action. Okay, so if I write an action like this, okay, this defines a theory. Of course, you know that this is just a machine that inputs in some set of physical principles, and it's an intermediary to that set of assumptions. So indeed, even the very definition of an action, which is an integral over one Lagrangian at one space-time point, not 2, 3, or 4, has input an assumption of space-time locality in my dynamics. Okay, that's just an implicit assumption I've put in. On top of that, you assume some degrees of freedom, you assume some symmetries which constrain the operators you write in your Lagrangian. Okay, those are all input principles. Okay, so again, I'm saying something obvious here, but there's some set of actual principles broadly defined which you're inputting into this. Now, what is everything that's not fixed by principles? Those have a name. Those are called free parameters. Okay, what is a free parameter? By definition, something that can take on any value because it's not fixed by principles. Okay, so from this point of view, the 19 or so free parameters of the standard model are simply the 19 parameters of the standard model that are not fixed by the principles that define the standard model, okay, which is why we have no recourse but to measure them. Okay, so that's the idea here, is that if you think about the principles and what's left, those free parameters are coupling constants, masses, and so on. Now, at the very end of this, we often think, okay, well, let's compute something useful, like some set of observables. Okay. This would be, for instance, a set of correlation functions or free energies. For me, it's going to be on-shell scattering amplitudes, the S matrix. Okay, that's the name of this this set of lectures. And we think of this, okay, we need to compare against data, check something. So this is what we do. Okay. Now, if I had to say in 2 minutes, what does the modern S matrix program, the modern amplitudes program do? We want to go directly from principles to observables without the use of this kind of intermediate paraphernalia. Okay. Now this should seem ill-defined. What does this even mean? Like to start from principles, go to the answer. Okay, it's the dumb thing you think it is. Okay, it's write a space of functions which your observable could be. Okay, so in some circumstances this could be correlators or other objects, but for scattering amplitudes this could be like a function of Mandelstam invariance, and then sculpt out from that big function space some set of principles that you then choose. Okay? Now, of course, if you assume nothing, if you know nothing about the shape of your functions, you'll make no progress. So the art here is knowing what constraints your observables or what properties your observables have. Now, what's cool about this is, of course, you can rediscover old things. We'll spend kind of the first lectures doing that, relearning about things in QFT, but if you like, without this middle step. But what's also interesting is that you can rule out things in the abstract. So what I mean by this is, let's say I told you 7 principles, and I said, write a theory that has these 7 principles. You might just keep guessing Lagrangians and toying with it and trying to figure out some, beautiful answer, but you may not make progress, but not know if such a theory exists. If instead you construct the observables directly and then try to constrain them with principles, you could learn that there is no function that can exhibit those principles, and thus you've ruled out a space of theories, if you like, in the abstract without making reference to some underlying Lagrangian. It's more powerful in that sense. So you can rule in and you can rule out. Okay, that's the basic idea. Now, okay, a fair question at this point would be, okay, why am I putting one hand behind my, why don't we use this? This is great. Lagrangian fields, they give us immense intuition. This is, modern quantum field theory. What possible advantage might we have by not using this? Okay, and there's 2, okay? Or there's 2 reasons you might not want to use an action or Hamiltonian or the usual formalism. The first, you'll know if you've ever done a calculation, from, let's say, even perturbation with Lagrangians, which often means Feynman diagrams, which is that there are massively complicated, complex objects, huge numbers of terms. I'll unpack that a bit very shortly, but the point is it's just cumbersome, okay? And as we'll see, the final answers are much simpler than the intermediate steps that go into that calculation, okay? So just, practically, at the level of just doing things, it's not so great always to use this method. But that leads you to the second reason, which is really the reason I'm interested in it, which is that when you have huge monster expressions which are complicated, they obscure structure. Real, legit structure that you will see with your eyes as we discuss this and maybe more importantly, structures that are not visible or at all obvious in the usual Lagrange interaction principle formulation of quantum field theories and theories in general. Okay, so the idea is that we're going to find structure directly inside the observables, and these, in many cases, and this will be maybe more the latter part of my lectures, simply have no explanation from like symmetry action principles. Okay, some do, but many don't, and that's what's kind of intriguing. By construction, if you work in a Lagrangian free way, you can learn things that you would never learn by just staring at the Lagrangian. Okay, and I will unpack in detail kind of what I mean by that. Okay, so let me start with the first point because it is well, it's a little polemical, but I feel like I should mention it. Okay, which is just something you know, which is Feynman diagrams are incredibly complicated. Of course, you're all grown-ups here. You've worked through all the exercises in Peskin, so you've computed scattering amplitudes in gauge theory, Yang-Mills theory. Okay, presumably 2-to-2 gluon scattering. One thing that most people probably haven't computed is the next to simplest process, 2-to-3, 5-particle, 5-gluon scattering. Okay, and I'm going to show it to you just to make an illustrative point. Okay, so like at tree level. Okay, tree level 5-gluon scattering. If you compute this using the usual rules in Peskin and Schroeder, whatever textbook you like, what do you get? Well, you get things involving, okay, I write this schematically, inner products of polarization tensors, inner products of momentum polarization, and then Mandelstams, okay, things like this, plus hundreds of terms. Okay, I think there's like 25 Feynman diagrams. You expand it out, you get a big old mess. Now, if you didn't know anything more than what's in many canonical textbooks, this is just the right answer, these hundreds of terms. But hopefully, at least many of you, I'm sure, know enough that this is actually drastically more complicated than the true physical answer for physical scattering. Okay, now for physical scattering, what I mean is a statement that we need momentum to sum to 0. Okay, it doesn't make sense to consider off this momentum conserving surface. And I'm also going to be considering on shell conditions, okay, and the usual conditions for polarizations, but the statement that the momenta are physical and the polarizations are physical. Okay. Now, if you actually do that and study this crazy messed up function with many terms for physical kinematics, you find something very, very famous, which is that it's the answer. So this amplitude A5 is actually much simpler than this hundreds of terms. So for instance, if you set every helicity, okay, so I'm implicitly working in 4D just for the moment, but we will leave the safety of 4D a little bit later. If you select all the helices and set them to all minus, or if you set them to all plus, then it's actually 0. Okay, which is just a statement that this is a big ol' rewriting of 0 in some complicated way. There are, of course, non-zero amplitudes. These are called the MHV, or maximally helicity violating amplitudes, one of which looks like this, 4 plus 5 plus equals, okay, 1, 2 cubed, 2, 3, 3, 4, 4, 5, 5, 1. Okay, now I've introduced some kind of angle bracket symbols, which I'm going to unpack towards the end of this, well, maybe towards the latter part of this lecture. These are called spinor helicity invariants. Okay, these are just kinematic variables that are just as good as P1, P2, P3, P4, P5. Okay, so I'll be writing like angle bracket and square bracket objects. Don't be scared of them. The point is there's no buried bodies here. These are very simple functions. That complexity hasn't been like repackaged in some crazy way. These are very simple functions of the original momenta. Okay, now what's the point? The point is it's hundreds of terms contracted to a monomial, which is what is known as one example of what's called the Park-Taylor formula, which is a formula for n-particle tree-level gluon scattering with 2 minuses and the rest plus. Okay, so this is simple. This is like, you just see with your eyes, something nice is going on here. Okay, so point 1, this is way more complicated than the answer. We should find ways of computing this directly. Okay, that should already be evident. There should be some way to get to here without going through here. Okay, but maybe the bigger point is that if you just look at this, there's structure. Okay, this already hints at structures that are already fed into multiple branches of ongoing research. So, I'll just mention a couple. So famously, in Witten's twistor string, he realized that this very compact function looks like a curve localized on a line in twistor space. Another example is folks who, right after this formula, realized it looks like a correlator, 2D. Okay, the WCW model, this was pointed out by VP Nair like a couple of years after this formula was written down. This is one of the seeds or one of the kernels of celestial holography, which looks at objects like this and says, wait, is there a CFT living somewhere inside this? Okay, so there's structure here. Okay, I'm not going to talk about those many different outgrowths, but the point is if you just stare at the answer, you might be able to learn something. Okay, so that was the case of gluons. Let me make that clear. This is gluons. You might think, okay, well, that's fine. Gauge theory is beautiful. It's amazing. Of course, things are simple. How general is this feature? Okay. Well, we can look at gravitons, okay, which I'll talk about a fair amount in this set of lectures. Okay, this way we're on the same page. I'm sure you all know what I mean. But what do I mean by gravitons? So by gravitons, I mean we're going to take the Einstein-Hilbert action, okay, and we're going to take g mu nu, and let's say expand about flat space. So this is eta mu nu plus some h mu nu, and then we do perturbation theory on this degree of freedom. Okay, so physically you can think of it as a scattering amplitude of gravitons is an amplitude that describes kind of the order by order nonlinearities of GR that affect linearized gravitational plane waves. Okay, scattering. Okay, so that's one way to think about this, but that's what I mean when I say graviton scattering, very mechanical. But we can ask for the case of gravitons in parallel with the case of gluons, how bad are things? And it's so bad that I can even start at 4-point. Okay, so if you rate the Feynman rules for this, which most folks haven't even seen, they're horrible. With the kind of canonical de Donder gauge fixing, yada yada yada, you got an expression I can't write on the board, but it's roughly 100 kilobytes on a computer. Okay, so I'll leave that as an exercise to you. Please don't text your answers. Please handwrite them. Okay, so it's obviously way more complicated than what the real answer is going to be, which is unsurprisingly, insanely simple. 1, 2 to the 4th, 3, 4 to the 4th. Again, using these so-called spinor helicity variables, which I'll unpack, and Mandelstam's. Okay, compacts to a monomial. Something magic is happening again. Also, in this instance, I should mention, it's not super well known, there's also a formula, closed formula for n graviton scattering with 2 minuses and all pluses, written down by Andrew Hodges many years ago already. Okay, so what's the reason for complexity reducing to simplicity? Well, you all know, hopefully, but let me just say it in 2 short equations. It's, of course, gauge symmetry, right? With the pros and cons of gauge symmetry. The point here is in the gauge theory, for the case of like Yang-Mills theory, the point is we like local Lagrangians, like that L of x I showed you before, but we also like Lorentz invariants. Those are, of course, properties of the final answer, but we're greedy and we want every step of our calculation to manifest both. So we introduce a 4-vector of x, right? Okay. But too many degrees of freedom, yada, yada, yada. We had to cut down those degrees of freedom by imposing some gauge symmetry. Okay, common story, that's what this redundancy is. It's a statement that there's a redundancy at the very start, which then imposes Ward identities, Ward-Takahashi type identities, on the final amplitudes, which takes terms and relates them, which is why there's way more terms than you actually need. Okay? And similarly for the graviton, okay, at least at the linear level, I'm not going to bother writing it out. There's a linearized this is the linearized diffeomorphism of the symmetry of gravity. Same story. There's too many degrees of freedom. You got to cut them down. Now, this story may make you feel like you're safe if you only cared about things without gauge symmetry or without diffs. Okay, so let's say you only cared about scalars. Okay, you live like a blessed life. You only care about like Higgses and pions and inflatons. Okay, you're like, oh, I'm great. None of this matters to me. That stuff is what you see is what you get. No gauge symmetry. It's all good. That is not true. In fact, let me just keep moving. Yeah, I'm kind of using board space quickly, but that's okay. In fact, I'd like to present this kind of particularly demented example, and we're going to return to it throughout these lectures, of a scalar field theory with an enormous redundancy in kind of a similar respect. Okay? So we're going to actually do a calculation. All right, so let's consider this Lagrangian. Okay, 1/2 g of phi, d phi, d phi. Okay, a 2-derivative Lagrangian, where g of phi is some arbitrary function of phi, which has an expansion about 0. Okay, so this is, of course, an effective field theory. This is not ultraviolet complete. There's nothing, completely complete about this theory. I'm not claiming that. But the point is, this is an effective field theory that you could write. Okay. And the point is, this is just an arbitrary series expansion about the origin, lambda 1, lambda 2, lambda 3, and so on. Okay. Now, the key point is, I am not assuming anything about lambda 1, lambda 2, lambda 3. Those are arbitrary coefficients. Okay, so if someone wrote down this theory, you would say, OK, this is a fine theory. I'm sure there's lots of interesting dynamics, right? It's like literally an infinite set of interactions. Let's compute something. Let's see how rich this theory is. Okay. Right. So what do we compute? Let's compute the first thing you'd think about in this theory, which is the 3-particle amplitude. Okay, 3-particle amplitude comes from d phi, lambda 1 phi. Okay, so you compute that. Hopefully I can get these factors right. If not, I'll fix them in post. Okay, but you have P1, P2, P3, plus P3, P1. Okay. Oh, great, that's the answer, right? Okay, that's the amplitude. But then you remember on-shell conditions. Okay, on-shell conditions tell us that, of course, pi squared equals 0. But also for 3-particle kinematics, if I have pi dot pj, I can write this as pi plus pj squared minus pi squared minus pj squared divided by 2. Okay, so I'm just rewriting this algebraically. Pi squared cancels that, pj squared cancels that. I get the cross term divided by 2. Now here's the problem. This is 0 on shell, that's 0 on shell, and this guy is the other leg, which is also on shell. So this is 0 too, okay, for 3-particle kinematics. Okay, so secretly, this is also 0. This is 0. Okay, so that's maybe a little odd, but that's okay. You know, 3-particle scattering, it's a little weird, a little degenerate. Surely this is just some weird accident. Let's keep going. Oops, sorry, I don't want to break Tazzy. So let's compute A4, all right? Same deal, so what's A4? So there's a contact term, minus lambda 2, coming from lambda 2 phi squared d phi squared, okay? You write down what it is, you got 2 derivatives. It's s plus t plus u. Okay, you're already thinking, that's interesting. Okay, s plus t plus u. There's, of course, cubic exchanges, so this is this diagram. And then there's exchanges that look like the cubic exchange diagram. Okay, 3 terms like that, which look like, okay, let's get this right, lambda 1 squared over 4, again, s squared over s, plus t squared over t, plus u squared over u, okay, which is also s plus t plus u. And lo and behold, of course, s plus t plus u equals 0, it's 0. All right, that's 0. Okay, if you keep doing this, I'm not going to keep doing it. 5.6 point, 14 point. My notes I've learned is 5 trillion diagrams. They're all 0. Okay, on shell. What that means is they're 0 also in an interesting way. For a higher point, there's like these weird cancellations where like different topologies come in and they all magically conspire and they're 0. Okay, so what happened here? Okay, so hopefully some of you know that there's a reason for this. This is just like some random thing. Okay. It boils down to the fact that, here's the field theoretic way of understanding this. Let's move on to this, which has to do with something called a field redefinition. Okay, so this again is something in textbooks, but let me just spell it out because maybe some folks haven't seen it for whatever reason. Okay, but I can do the following. Take phi in a Lagrangian of your choice. Okay, this happens all the time in effective field theories, maybe less so as you percolate out of that community, and send phi to f of phi, okay? Subject to the constraint that f prime of 0 equals 1. Okay, so if I were to write this maybe like perturbatively, it would be like phi, which is that 1, okay, plus stuff which is nonlinear in phi. Phi squared, phi cubed, phi to the fourth, whatever. Okay, anything you want. Okay, I'm just making this a random arbitrary function in these dot, dot, dots. Okay, now this is actually, as it turns out, if you do this, your Lagrangian does not stay the same. The claim is not that this is a symmetry. It's not a symmetry. The Lagrangian changes, but you can see for yourself that there is a choice for this where, what I call L, okay? There's a choice of f, okay? If you just plug this into L, for which L maps to 1/2 d phi squared. Okay, first statement. I can map that very complicated Lagrangian into a free theory. Okay, I'll leave that as an exercise to you to see. You just have to choose F in some way that's aligned with those lambda 2, lambda 1, lambda 2, lambda 3. You can do it all orders in phi. Okay. Now, why is that allowed? Okay, this is not a symmetry, but I'm saying the S matrix, scattering amplitudes that you measure, are invariant under it. Okay? And the point here is that it's a coordinate transformation. It's a gauge symmetry that's secretly in the back we never talk about. You do this all the time in classical mechanics. In classical mechanics, you start with a Lagrangian that's in Cartesian. You transform it to another Lagrangian that's different in polar. They do not look the same. Okay. But if you compute something physical, okay, like a binding energy or scattering angle, something like that you'd measure at asymptotia, those do not care which coordination you use. Now, of course, there are observables that do care about your correlators, like a bulk correlator. You're doing like cosmology, or you just care about bulk objects. Then they care, and then you have to covariantly map your observables. So you just have to do everything correctly. You change variables correctly. There's also, of course, Jacobians, other things you have to care about. But the point here is that the path integral is a path integral over fields. Your choice of coordinatization of your fields is being integrated over, so you can change variables. Okay? That's the obvious statement, which is why this is an invariance of all or covariance of all observables. Even more nicely, for the case of S matrix amplitudes, it's an invariance. Okay, let me say this quickly, just because that might be confusing. You might ask, why is the S matrix literally invariant and not covariant? Well, this stipulation that there's a 1 here mandated that my one particle states were unchanged, and those are the states at asymptotia that I'm scattering. Okay, so another technical way of saying is that LSZ projects out all these dots. I'm happy to go through it in more detail if someone has questions after. Okay, but the point is, you can do a field redefinition to map Lagrangians to equivalent Lagrangians with impunity. Okay, and that's kind of good and bad. Okay, so I'm just gonna write this explicitly. Okay, imagine that in your copy of Peskin-Schroeder, there's some Lagrangian that we all use for, let's say, Yang-Mills, L1, or phi-4 theory, or whatever. I can map it to a new Lagrangian with a field redefinition. Okay, this is kind of a even more extreme version of gauge fixing differently. Okay, except it's about the field variables themselves. L2 will not look like L1. Okay, and of course I can go to L3 and L4 and so on, L infinity. There's an infinite number of Lagrangians that all contain exactly the same physics information, because they're different coordinatizations, the same stuff. But of course the point here is that they all map to the same on-shell S matrix. Okay, so that's like a many to one, many infinite to one mapping. Now, let's say you wanted to find new structure. Like, I don't know, you're just interested in structures in QFT. Well, you could hunt in the Lagrangians. You could like keep mapping, try to find the analog of spherical coordinates, just keep trying. Okay, that's a pretty tough task because there's an infinite number of them. Or you can just cheat and just go to the final answer and just look for structure there. Okay, this mods out by the gauge redundancy, by the field basis redundancy, and that's exactly what we're going to do. Okay, so the idea here is that by bootstrapping without L, Lagrangian-free thinking, and then looking at the answer, we'll just find non-obvious structures. I think even in the next maybe 10 minutes, we'll see some relatively maybe surprising structures to you if you just stare at Lagrangians all day. Okay, good. So that's where we're going. Again, just one more comment, because I want to give you an outline of what we're doing, but also give you a sense of the kind of broad things that we've learned, because I'm still talking a little bit in the abstract about these structures. And where are we at? What's the value added of staring at these objects' amplitudes? Well, they kind of break into two it's not artificial, but two kind of classes of things we've learned, which from amplitudes I'll call structure and applications. Structure is structure inside theories, inside S matrices that have no real concrete explicit understanding from the point of view of Lagrangians. Okay, so it's like an opportunity. Things we don't understand why they are present, but wouldn't it be great if we could understand them? Let me list a couple, and I will talk about them at length later. One, which is really one of my favorites, is something called the double copy. Okay, and let me just tell you what it is in words. Okay, the double copy is a statement that if you have already computed all the gluon scattering amplitudes in some intelligent way, you have all gluon gauge theory amplitudes, you can literally square them and add them. Like the operations of adding and squaring, you can use that to combine them to get graviton scattering amplitudes. Okay, now that isn't a like, oh, conjectural, like that's kind of cool, maybe this might work. It's a fact. It's a fact mathematically about the amplitudes. It's a cheat code for building gravitational observables. Okay, so it's the kind of lesson I have to say is it tells us the easiest way to compute in gravity, which is don't compute in gravity. Okay? Compute in gauge theory, and then square it, okay? And we really believe that, and we've now used, I mentioned this in applications, but there's some interesting new applications of that idea. But this also is well known in the case of gauge theory and gravity. What's less well known is this true for other aspects that show up, or other theories that show up on hep pH and hep TH. So for instance, it also holds for pions in the chiral Lagrangian. It applies to Galileans, which show up in cosmology, Born-Infeld, like lots of theories you kind of know, you've heard about. They're all weirdly connected and linked through this structure, which hopefully I'll have a lot of time to talk about in even the third and fourth lectures. Okay, that's one thing. Okay, I will definitely harp on this, but I felt like I should mention a couple others, just because you've probably heard about them. Call this polyhedra is my catch-all for things like the amplituhedron, which I'm sure you heard about from your aunts and uncles from the popular press, and like the associahedron. My grandma was like, what's that? Okay, so what is it? What are these? I'm not going to talk about it, but I can tell you in one word what it is. The idea is take an amplitude, which is some beautiful invariant object, and think about it as a volume in some abstract auxiliary space. Okay, so from that point of view, it's like a volume. And to compute a volume, you can chop it up in any way you like. If you chop it up this way, it's Feynman diagrams. You chop it up this way, it's recursion, which is something I'll mention later. If you chop it up this way, it's different. But there's some invariant notion of a volume. And as it turns out, in certain special theories and certain not so special theories, there's just a way of thinking about the amplitudes as volumes. That's pretty cool. Gives a different understanding of what an amplitude is. Okay, I will not talk about that at all, but I thought I should mention it. There's, of course, also the celestial program, which, again, I don't need to talk about because Andrea has her beautiful lectures on that. So kind of celestial amplitudes and celestial holography, which connects with this fact that there's enticing structures that look weirdly holographic in gauge theory scattering and graviton scattering. Okay, that's one. Okay, there's an infinite list of things that will not do justice, twistor theory, scattering equations, yada, yada. Okay, all these things, there's no like instruction manual in the Lagrangian to tell us what's going on, but their structure. Okay, so that's the kind of enticing new features. Then there's just like brute applications, which I think are also kind of cool. Okay, maybe this isn't the right crowd for that, but some of it, I don't know. On occasion, we like to like apply things to things that might even connect with experiments. I can't say that here. I'm sorry. I'm sorry for mentioning experiments. Okay, but do more. Okay, good. I got one person on my side. So colliders, of course, we compute amplitudes because they're important for scattering at the LHC. And super colliders, that's of course an old story. Maybe slightly less familiar, but also old story is supergravity. Of folks like Zvi Bern long ago and continue to compute high loop perturbative gravitational amplitudes to try to study and understand the UV properties of this theory. Okay, this is kind of the old story. More recently, though, and by this I mean since maybe last time was in TASI, there have been other applications. Maybe one of the big ones is the application of cosmology. This was really pushed forward by Nima and Dan Bauman, where they use kind of these bootstrap ideas to build correlation functions in the early universe. In some cases, wave functions of the coefficients of the wave function of the universe, and so on. Okay, that's an interesting connection. And then two other things which I'll actually talk about. Okay, so one is called positivity, which you've probably seen and heard about on HEP-TH. The basic idea here, when I say positivity seems very vague, is that using amplitudes constraints, you can constrain Wilson coefficients of effective field theories in super non-trivial ways. Okay, there's a weird kind of UVR connection that is provable and derivable to tell you that certain effective field theories are inconsistent, despite what you might think. Yeah, so I'm gonna try to get to this in my lectures. We'll see. There's been a huge amount of progress and understanding of this topic since I was last here. And then the last thing is gravitational waves. Okay, this was again a pipe dream maybe 5 years ago, but I've already kind of told you that there's a cheat code for gravitational observables. okay? And at this point, that bridge has been gapped where we can compute observables corresponding to the scattering of massive black holes in GR, Einstein's general relativity, and we can map that to the Hamiltonian for two black holes in binary inspiral, or actually even neutron stars, if you want to include tidal effects. And at present, the state-of-the-art calculations in G Newton, in perturbation theories in G Newton, is done with amplitudes methods, okay? So there was a leapfrog where we were catching up, and now what's called post-Minkowski in perturbation theory is amplitudes applied to this problem, and it has, I think, had some good mixing and synergy with the existing gravitational wave community. Okay, so this is my really quick overview of the cool magic that pops out, and then how to make a better toaster out of it. I think at this point, let me outline what I'm going to cover. Yes.
So in your scalar field example, you used the Symmetry definition to show that hidden structure could be rewritten in terms of another local Lagrangian.
Yeah, right.
But nothing like that is going to be true for a gauge theory, right? You're not going to be able to find some field redefinition that makes all this stuff matter.
No, yeah, for sure, yeah. So the question was, does this work for a gauge theory? The claim is not that every theory is free. Okay, I'm definitely not claiming that. Okay? Maybe if you're a topological field theorist, but the S matrix is not vanishing. This is a special theory. In fact, we're going to come back to this theory and understand it 3 different ways in various one-liners, why these all vanish. Okay. For gauge theory, it's not true. Even if you add multiple scalars, things get complicated. So indeed, it's not. I'm not claiming that all S matrices are vanishing. Yes.
Yeah, but since Oliver has said something, I'll go to the other point, which is that all of this field redefinition is extremely important for standard model effective.
Absolutely. Yeah, I didn't know if I should mention it here, but absolutely. Thank you for bringing that up. In the standard model EFT, or in the effective field theory of GR, where you have higher curvature corrections, or any theory where you have a derivative expansion, this understanding of field redefinitions is crucial. Okay, it's so crucial that in experiments, you might confuse yourself that you're measuring an invariant object when in another gauge you're measuring something which is not invariant. You can already see that a coupling, lambda 1 is not physical. If you told experimentalists, go measure lambda 1, and they say, yeah, I measured it, it doesn't really make sense because it's related to everything else by field redefinitions. You have to be careful with this. So absolutely, effective field theories broadly in any context have this property also, but anything with a path integral has this property. Thank you. Good. Yeah. Yeah.
So here you made the impression that the complexity comes from the gauge redundance.
Yeah.
But it's also true that the amplitude above it actually contains more information because it could be part of some more complex diagrams that you are using, right?
Sure. Absolutely.
Here you're kind of lost in.
Good. So you'd say, wait a minute, don't we want this off shell so I can jam it into a higher point diagram?
Yeah.
For sure. Absolutely. And practically, in many cases, people use things called Barons-Gila recursion, which are semi-off shell to do this. But the point is, if you tried looking for structure in that unphysical object, which is gauge dependent, it won't get you very far. But for sure, at a practical level, this is still useful because you can feed it into 6-point, for sure. Yeah. But the idea here is you could also just compute 6-point, which turns out to be 1 or 2 terms. Okay, so the methods that get you directly here can also get you 6-point, and I'll talk about those. But yes, cool. All right, yeah, I gotta get to some real meat at some point. But yeah.
Coming to the theme of the code, so related to double copy, so you compute symmetry amplitude, which we also know that they're constrained by more entities.
Right.
And even at the quantum levels of the bulk.
Right.
Then the claim is that if I take 2 amplitude, I square them, I get an amplitude for gravity. And presumably, we want to the same gravity, and you also use decomposition. You should also not have global.
Right. Right.
So how should I?
Those are awesome questions which you'd answer, and you need to answer by first understanding the QFT behind the double copy. But here, but let me just follow up on the question, which was about how the double copy maps things into gravity. And given that gravity, we think there aren't global symmetries, and gravity, there's some notion of a mystery of how it's ultraviolet completed at high energies. Can this illuminate that? Okay. And I don't have an answer because we don't have a crisp, here's the mapping and the explanation. But this tells you why the stakes are high. If you have a mapping between gravity and weak coupling and gauge theory at weak coupling, okay, this is different than ADS-CFT, that's an intriguing possibility. If it was somehow non-perturbative, true in arbitrary backgrounds, this and that, it would be super powerful. Now, I don't think that is going to be the case. I will, for various technical reasons. I think it's definitely true, of course, classically for tree level. But the stakes are high, okay? Like mapping gravity to something that's not gravity is an interesting, very interesting opportunity in principle. Yeah. Okay, good. We're gonna keep going. Yeah.
This is map valid for, does it work at one loop?
Good. So are we talking about double copy? Good. Yeah. So double copy, and again, this is going to be all of the third lecture anyway. This is proven at tree level, recycled into one loop through unitarity methods. So what's funny is that in amplitudes, this distinction between loop and tree is more porous because the way we build loops is by constructing them from trees using these bootstrap methods. So it kind of gets fed in through that. But it's a longer discussion, which I'll get into, I think, when I actually cover that here. In fact, let me now take the opportunity to actually tell you what I'm going to cover, okay, in very broad strokes. So one, okay, this is like, there's going to be 3 rough parts. Sorry if I'm already late. The first is just going to be a bootstrap tutorial. Okay, kind of doing what I said I was going to do. We're going to relearn lots of old things, maybe learn some kind of cute new things. Okay, but this is going to be relatively simple. Yeah. Okay. Once we have those basics down, I have no better way of describing this, but I'll call it IR and UV. Okay. The idea is we're going to take those bootstrap principles and apply them to scattering amplitudes in special kinematic regimes. So one kinematic regime that's interesting is the infrared, which means that you take one external particle or some number and you just make it low energy, soft, that's what we call it, low momentum, and study its properties. Okay? And we'll learn things that you know, but from kind of an oblique direction. I'm going to talk about things called soft theorems, which is a statement about universal properties when you take an amplitude and take one of its particles to be low energy. Okay? So we'll talk about that. And then I'll mention interplay with the ultraviolet. So this will be the story on positivity, where with these ideas all together, we're going to show how there is relation between UV and IR. The Wilson coefficients of a theory in the infrared are intimately tied and constrained by assumptions about the theory having UV completion. Okay? And these will be general statements that are Lagrangian independent. Okay? So that's where we'll go next, which is kind of like the next level of this. And then the last thing I'll talk about, hopefully I want to spend the most time on this, is hidden structures, which will be largely about double copy, but will be about how particles like gravitons, gluons, pions, galileons, Born-Infeld photons are all tangled up and related to each other in like a direct, explicit way. You don't usually think of gravitons and pions as connected, but they're deeply connected. Okay, and I will talk about that. And then here at the very end, I really hope I can get to this. We're going to do like an Empire Strikes Back type thing where QFT is going to come back. Okay. The bad guy is going to come back as a good guy, and I'm going to explain some of these structures using Lagrangians. Okay? Now, that should definitely make me sound unprincipled and hypocritical. That's definitely what I am, okay, because I have no beliefs. But I would say what's key to know is that for some people, amplitudes is like it's like their whole identity, and they have to like wear robes and like, pray, and there's like charismatic leaders with long hair saying space-time is doomed. So that's fine, okay. But for me, it's a tool. Amplitudes is a tool. You like use it to like get work done. But once you find the structure, you can do whatever you want to figure it out, okay? Keep that in mind as researchers. There's no rules. Do whatever it takes. Use ChatGPT. Doesn't matter. You're actually trying to figure things out that other people don't know, so you can do whatever you want. So you can come back to this with QFT, and I will show you how things like the double copy, for instance, for the case of pions, has a QFT understanding. Okay? The level of Lagrangians, fields, currents, we'll understand something a little bit more about that theory. Okay, so that's hopefully what I will attempt to reach. I'll probably cut things in order to get to it. Okay, good. If there aren't any pressing questions, let me push forward. How much time do I have?
You have about a half hour.
Okay, good. We'll never make it. Okay, let's start with the bootstrap tutorial. This is going to be, much less flashy. We're going to like be bare bones and simple about things. I have to outline the assumptions, and I want to do that relatively thoroughly right at the start. Don't worry, there aren't a lot. Most of them are obvious, but the way I state them will, I think, hopefully tell you the kind of approach we're going to take. Okay, skip. Okay, what are our assumptions for the bootstrap? So the idea is like we start with a space of functions. That space of functions is constrained by some set of principles. What are the principles? Okay, first principle, dimensional analysis. Okay, not normally a principle we would say, but I have to kind of spell it out a little bit more here. What do I mean by that? Okay, get an equation. If you take the n particle scattering amplitude, okay, including coupling constants, momenta, everything, but stripping away the delta function, this has some dimension, capital D plus n minus capital Dn over 2, which for D goes to 4. It's usual 4 minus n. Okay, the point is, this will be important to us, because like we're computing a quantity, we should know its mass dimension. Okay. Now, of course, there's also couplings. Sorry?
What did you say? What n was?
Sorry, n particle scattering amplitude in capital D dimensions. Sorry, thank you. Okay. Now, what is an amplitude made of? Momenta and coupling constants. Okay. So you could, if you like, define, start with a presumption that your coupling constants have a fixed dimension. So if you had a preference like I want to bootstrap a gauge theory, you can start with the preconceived assumption that the coupling in play is dimension 4 minus d, as would be in the d-dimensional gauge theory, which for d goes to 4 is 0. Or let's say if you were looking at gravity, you might just say, oh, I want a coupling with this dimension, which in t minus 4 is minus 2, which is just 1 on n Planck squared. Okay, so you can think of it that way. But of course, as soon as you fix the couplings, all the other mass dimension is momentum. Okay, so if you've decided to fix the dimension of the coupling, you've implicitly fixed the number of derivatives, or momenta, sitting in front of your amplitude, and also the converse. Okay, so if you didn't want to make reference to couplings, because you haven't learned about these yet, you don't have a Lagrangian, you could assume some power of momenta, okay, and that implicitly fixes some dimensionality of your coupling constant. Okay, it's a two-way street. Depending on what we're doing, we'll do one or the other. Okay. All very basic. Okay, cool. Let me put this in one okay, so that's dimensional analysis. Second is, I'll just call it exchange symmetry. It's probably not a good name for it. Okay, but this is just a statement of spin statistics, taking as an input, which is that if you have identical bosons that are scattering, then if you swap them, the thing's invariant under it. If you have identical fermions, then you swap and you get a minus sign. Okay, that's all I mean by this. We will also kind of use this as a two-way street. Sometimes we'll be like, I want to bootstrap a theory of identical bosons, and that will enforce this as an isometry of the function we're building. Other times, we'll impose other physical principles and learn that an isometry comes out, and then deduce what kind of particle we were talking about from the start. Okay? So as usual, these go both ways, because we're kind of assuming less. Okay, so that's exchange symmetry. Lorentz symmetry, or Lorentz invariance. This is a kind of an obvious one. You don't technically need this. You could do this with less symmetry if you like, but it's just harder. All I mean by this is that when we build amplitudes, they'll depend on invariance. Okay, so if you were, if you like Mandelstam invariance, maybe pi dot pj. If you've, for whatever reason, deign to use polarization vectors, which intrinsically still have a redundancy, but you could still bootstrap this way, you'll have a function made of these Lorentz invariant products. Okay, that's one example. But as we're going to see, a much kind of nicer, cleaner way to do this is to use these angle and brackets objects, spinnerlicity variables, but these are all like just different versions of how to parameterize your kinematics. Okay, they all have different advantages. Okay, good. Last but not least, and I think this is really the most important, this is the constraint with the most teeth, and the one that's the most, really gives the most implications, is factorization. Okay, and I'm kind of implicitly thinking about this in terms of tree level. Okay, just because we're going to be doing perturbation theory, we're going to kind of crawl before we walk. What do I mean by factorization? Oh, sorry, this is really messy. By factorization, I just mean that let's say someone writes down a putative 4-point function. Okay, this is just some function of s and t and whatever kinematic variables you have. Okay, Now, I want to sculpt out from this a consistent amplitude. Well, one property it has is I know that if I take two momenta, let's say in the S channel, and I just tune them, I tune them to be on resonance with some intermediate exchange particle. Okay, let's say I have mass m squared, and I take S goes to m squared. This thing should degenerate on that residue into two subprocesses. Okay. There's a minus sign here, just so it's not a ghost, but here, this is A3, this is A3, and this particle in between has mass m squared. Okay, it's just like the grown-up version of the statement that when you go on resonance, right, like resonance of energy levels, you have some blow up of the amplitude corresponding to the fact that this intermediate particle is on shell. Okay, this is the intermediate particle going on shell. Of course, we even know physically what that is. If you write this propagator in Schwinger parameterization, some like long d tau effect. Okay, so it's like literally the infinity from like traveling a great distance in space and time. Okay, so it's just an input. Okay, this is what lets us relate higher point to lower point. Now, this is not a Feynman diagram. I want to emphasize this. This is not me just like sneaking it back in. Because the statement isn't that I'm just like multiplying 3 particles and getting 4 particles. The statement is that 4 particles at special kinematics, a very specific place, degenerates into this product, which then lets me place a constraint on that ansatz for A4. Okay, we're going to do that in a real baby version shortly. Okay, corollary to this, which I'll mention, it's not quite factorization, that's actually kind of a weaker assumption. So sometimes this assumption is called locality. It's a really bad nomenclature because it makes you think of like rigid technical things like macrocausality, microcausality. It has nothing to do with that. We, for some reason, use these words. But the idea is that if you have a 1 on S squared, double pole, or 1 over S minus M squared, okay, then the residue will be divergent, okay, and that's inconsistent with it properly factorizing. So we just don't have these objects. Okay, so if you take a residue, it should give you a finite answer, which is the product of the two adjoining amplitudes. Okay, so that's our input. Very good. Okay, that was good. That was fast. Cool. All right, let's just start doing things. Okay, so let's actually bootstrap some things. Okay, and again, I apologize because we're gonna like I said, we're gonna learn to crawl before we walk, but it's really like learning to breathe before you crawl. So we're going to start with this, what we'll all agree is the simplest QFT, which is scalar field theory. Okay? All right. We'll start with scalars, and we're going to bootstrap it at 3 and 4 point with these ideas, and maybe even learn something like next to, not quite trivial, but next to trivial, about scalars. Okay. In fact, this will be a path to giving a one-line explanation, not one line, 2-line proof for why this is true. From the point of scattering, not from the point of a Lagrangian. Okay? Good. So let's talk about scalar theories. Okay? And we're going to start at the ground floor here. 3 point. Okay, there's almost nothing to say here. We kind of already know what's going to happen. What is A3? Well, it's a scalar. So everything only depends on P1, P2, P3. All inner products of P1, P2, P3 are 0. So there's no P dependence. So the only thing this can be is a constant. Okay, proof. This is a constant. Okay. Now, you might immediately, okay, that's cool. This is like a phi cubed. That's what this constant is, phi cube theory. But wait a minute, something's funny. Something's missing. There was a whole class of theories that I thought existed that have derivatives in the 3-point interaction, right? Okay, so for instance, d phi squared times phi, just like that, first cubic interaction. I can just write this. What happened to this? Okay. Well, first the statement is, of course, we just checked that this would contribute 0 to the on-shell scattering amplitude. So you might say, okay, well, it's not in the on-shell scattering amplitude, but then you just missed something. Well, it turns out you didn't even miss something. Okay, let me tell you why. Okay, I can rewrite this by integrating by parts. Let me do it. I'm not going to show all the steps, but you can rewrite this as -1/2 phi squared box phi. You knew this had to be true because if you looked at the Feynman rule for this, it has to vanish on shell, so a box has to end up hitting someone. Okay, this is just a fancy way of me rewriting pi.pj as pi squared, okay, but at the level of Lagrangian. Now this is exactly the same Lagrangian, no changes, but for again, reasons that I'm happy to explain if you haven't seen this, when you have an effective field theory like this, or any theory, where there is an operator proportional to the equations of motion. Okay, where you could eliminate box phi through its equation of motion by writing it as box phi equals other terms. You can do a field redefinition that removes this operator, okay, and replaces it with some operator that's higher orders in phi. Okay, I'm not going to go through that here because it's relatively basic, but I'm happy to explain it later. The point is, this can be eliminated by field redefinition. There is a choice of gauge or field basis where this is not even present, okay, which is analogous to that slick field basis where we made everything 0. Okay, but this is really just for this cubic interaction. Okay, so what's the point? We've learned something kind of interesting. There is no derivatively coupled 3-point function, 3-point vertex for scalars. That's not like an invariant thing. I can always go to a basis where it's tossed up to 4-point, 5-point, or some higher point. Okay? It's still physics. It's still up there somewhere. It just is a basis where it isn't a 3-particle interaction at all. Okay? So that's what we learned by studying the amplitude, that there exists a basis where that vertex coefficient, that the coefficient is 0. Okay. Now, it should also be clear that this is all true even if I have multiple flavors. Okay, and also true if I have masses. Okay, I didn't mention this, but of course, if I added masses, a bunch of these pi squareds or m squareds, but m squared is a constant. Okay, so good. Okay, you can have m squared, but m squared is just another constant. So for any number of flavors of scalars with or without mass, there's only one 3-particle amplitude, which is a constant. Okay. Good. So that's a very simple case of 3-point. Let's do 4-point. Okay? And again, we're doing this because it's a really nice way to see structurally how the bootstrap idea works. Let's go to 4-point. How do we do 4-point? Well, for 4-point, we have to make sure it's consistent with 3-point because of factorization and all the other inputs. Okay, so to do this, let me write a 4, and if you like, write an ansatz for it. And that's what I said. I'm going to split the ansatz into 2 pieces. There's a piece which is the factorization piece, and there's a piece which is the contact piece. Okay, and what do I mean by that? So the factorization piece is the piece that's going to have poles in S, T, and U. Singularities, like 1 on S's, 1 on T's, 1 on U's. The contact piece is the piece that's going to be analytic in STU. If you like, a tree level would be like a polynomial STU. Okay. Okay. I'm making this kind of split. You can imagine that there's kind of many ways to think of like splitting something this way, but it doesn't matter. Just have coverage, and you'll be good. The idea here is that factorization, this a fact, is the only thing that has poles, so it's the only thing that needs to match A3. Okay, so let's write down what it is. So what can A4 fact be? Well, it's got to have a pole in S. So let's call this NS over S, and T over T, plus NU over U. Okay, this means just like putting a pole in S, T, and U. Okay, so like I've just defined it to have those poles. Okay, so I have coverage. Now, I then constrain it with this, let me leave this on the board because it's what I'll be using. I want to constrain this thing so that, again, I'm assuming, I should have said this before, but let me assume massless particles just for simplicity here. We want to say that if I take the limit where S goes to 0 of S times A4 factorization, and that's just this formula here, but with m squared set to 0, okay, then this should equal minus A3, A3. Okay. Yes?
Is there a clean way to see that amplitudes get factorized? Like that should be an assumption we would take without having done the whole thing with Feynman diagrams. Let's say it's just how the feature of the theories that we write down.
Can you repeat
Yeah. So, to repeat the question. Yeah. I think the question kind of implicitly was thinking like, this is a property of Feynman diagrams that's like, that we learn from Feynman diagrams. So Feynman diagrams have 1 on p² poles. But I would view it as like a property of almost like quantum mechanics. Okay, the statement that like if you insert a complete set of states, okay, between 2 processes, it breaks into 2 separate processes. It's a statement about quantum mechanics, right? If I imagine in state to out state, sandwich in an intermediate state on shell, that forces the external states to be at special kinematics, and then you get a resonance. So I would say this is a property of the complete set of states. So it transcends having Feynman diagrams. It's a statement that making this on shell forces these kinematics to be in some configuration, and then there's some phase space for this thing to propagate. So I think it's more general. But if you like, take the assumption any way you like. If you want to derive it secretly with Feynman rules, that's cool too. We're just going to use it as a tool. Yeah. I'm not a zealot about like how rigidly axiomatic these are independent assumptions. We're just going to use them. Yeah. But thank you for that question. Good. So here, this thing is just minus lambda squared. Okay. So what does this tell me? So this thing only has a pole in S in this first term. These are both regular as S goes to 0 because S plus T plus U equals 0. So what we learn is that NS, this is an equal sign? Yeah. Yes, sorry. I'm sorry. Yes, thank you. Thank you, that's an equal sign. I should be a little better with my handwriting. I apologize. Okay. Now we can take the limit. We can just determine what this means for NS. And it means that NS is equal to minus lambda squared plus things of order S, of order S. Because, sorry, I should say this. I should say this is just lambda squared, which means that NS is equal to minus lambda squared plus things of order S or higher. Okay, because when S goes to 0, these could still be there. Okay, now all such terms, linear, quadratic, cubic, and S, those terms that have powers in S will cancel the S pole. Okay, so I might as well just drop them because I could put them in contact. Okay, we would call this a pinch, but the idea is that these terms with like inverse propagators in the upstairs, if I put an S in an S, I could call it singular, but it's not really singular because it cancels the pole. It gives me 1. So I might as well just toss it into my definition of A4 contact, which is why I can, with impunity, just drop these terms. Okay, so this kind of cleans up the analysis a bit. Let me put this up. Oh, okay, maybe you don't need this. So what we've learned is that NS is lambda squared, which implies that a factorization is known. Just write it out here. A4 factorization is minus lambda squared 1 over S plus 1 over T plus 1 over U. Okay, just by doing it in all 3 channels. Okay, you already know this. This is just the phi cubed diagram, but we're getting it through an incredibly much more complicated approach, which for this isn't easier, clearly, than the usual story. Okay. But again, we're just trying to be instructive. Now, we can now move on to the contact piece, and this one's the really easy part. If I have something which is contact, that just means it's analytic and momentum, which means I just have to enumerate all polynomials in the kinematics. Okay, so if I have A4 contact, okay, what could it be? Okay, I just want to write down local functions of S, T, and U. In case I think I said this, but let me reemphasize. We're thinking about one scalar particle. Okay, that's why there's a Bose symmetry under exchange, S, T, and U symmetry. Okay, so I just want to write down something which is symmetric in S, T, and U, and is a polynomial. Okay, so what could it be? Well, it could be 1. Okay, that's one option. Okay, what else could it be? It could be S plus T plus U. Okay, that is to say, these are the quadratic and momentum invariant, which is permutation invariant. Okay? So I'm just writing options here. I'm not saying these are equal. These are just different options for the contact term. We could have S squared plus T squared plus U squared. We could have S cubed plus T cubed plus U cubed, which is actually equal to 3 STU. Many ways of writing this. Okay. Okay, so you can see this is just decomposed into a statement of building symmetric polynomials in 3 variables. Okay, there's a basis for that, which is these. Okay, but actually nicely, one of those basis elements is actually 0 because S plus T plus U equals 0. So what are these theories? Okay, if I just go back to the crutch of Lagrangians, what are these theories? Okay, let me draw them over here. So this one here is phi4. This is phi4 theory. This 1 means constant, of course. There's some free parameter in front of it, but it's phi4 theory. This one here is d phi squared times phi squared. This one here is d phi to the 4th. This one here is d phi squared, d phi squared. Okay, so we've enumerated different quantum field theories in this kind of painful way. Yes?
What about ST plus TU plus SU?
ST plus, that can be written as this. Yeah, good. So you might think there's ST plus TU plus US, but if you plug in for U equals minus S minus T, it's proportional to this. Thank you. But just generally speaking, this is the theory of symmetric polynomials, so you know there's a fixed basis. Okay? But I leave it as exercise to see that. But indeed, it's proportional to that. Good. So more super generally, all 4-point functions, all contact 4-point functions are a function of, I can pick a basis, but let's say s squared plus t squared plus u squared and stu. Okay, because the last symmetric polynomial is 0, so I don't include it. Oh, sorry, I shouldn't draw that low, but sorry. Yeah. Good. Okay, so these are all the names. This is just a way of deriving these. Yeah.
Why is dd phi squared not allowed?
d phi squared. This is present.
Like instead of d phi to the fourth.
Oh yeah, so you could have d phi to the, yeah, that would be fine too. So if you want to move schematically two derivatives elsewhere, yeah, it's all fine. So in fact, maybe this is a good point. You might get confused because there's many ways of putting these derivatives on, right? Like there's many different contractions. You'd be like, well, I can contract these, and I've been super schematic. But the point is, it doesn't matter which way you put them together. The only thing they can yield is this symmetric function, okay? Which means on shell, they're all the same. Okay. Now, of course, in actual theories, those contractions make a difference. What happened to that difference? Well, the difference evaporates from 4-point scattering and is actually at higher point scattering. So you've also learned something, which is the fine gradation between how you contract those indices does not matter at 4-point, okay? But it does matter at higher point because any field redefinition puts it up to higher point. Okay, good. So this is all, I think, relatively obvious. But let's return. Let's return to this example I gave of the disappearing amplitudes in that theory, which I've now erased. And I'll give you the amplitudes argument for why, obviously, that S matrix is vanishing. Yes? Yeah.
So shouldn't A4 have dimension 0? So aren't these towers automatically ruled out?
So the mass dimension of A4 comes from the kinematics, but also the coupling constants. So here I haven't drawn couplings. All those couplings absorb whatever dimensionality I want. Okay, so I could put like a lambda, lambda prime, lambda double prime. They just have whatever dimension it takes to absorb those dimensions. Yeah. Question? Yeah. So absolutely. So you could go s to the fourth, s to the plus t to the fourth plus u to the fourth, but you can rewrite it as these symmetric polynomials. It's the usual reduction of a general symmetric function in, let's say, 3 variables in terms of a basis of symmetric polynomials. Okay, what is it, like Vieta's formulas or whatever from Galois theory? Good. Okay, so let's return to that theory I wrote. And we're going to give a one-liner from the point of scattering for why this is trivial. Okay, it's going to be inductive proof, very simple. Okay, the only real work is you have to compute A3, okay, which we've done like 7 times now. This is 0. Okay, good. So that's the like induction step initialization. What's A4? Okay, well, A4, as we decided, has a factorization piece and a contact piece. Okay, the factorization piece is going to be proportional to lower point lambda. Okay, but we just decided that A3 is 0, so there is no factorization piece. There's only a contact piece. Since there's only a contact piece, I know from first principles that this has to be proportional to s plus t plus u by dimensional analysis. This is the only object that has 2 derivatives and is symmetric, so it's 0. Okay, good. So A4 is 0. Easy. Now we go to A5. Well, same argument. What is A5? A5 has a factorization piece. Okay, factorization into lower point amplitudes, which you can just put in. It's more complicated because you have 2 propagators, but you can just build it, and a contact piece. But I already established that A3 and A4 are 0. There is no factorization piece. Okay, so A5 is also pure contact. It's pure contact. Okay, so what is this? It's got to be something which is symmetrical, linear, quadratic in all the momenta, and permutation invariant. In fact, let me just jump to endpoint. At endpoint, the only object you can write is some version of sum of pi pj, summed on I and j, which is proportional to the sum over pi of I squared, okay, on on-shell conditions. So the same is just write down local symmetric functions and momenta that have 2 momenta, and you'll just find they're 0. Okay, so by virtue of the fact that the contact terms are 0, we then deduce the entire S matrix is 0. All the factorization pieces vanish, and then we clean up with the contact by just computing it and seeing that it's also 0 on shell for any endpoint. Okay, that's slicker than knowing what field redefinitions are. I mean, it allows you a different way of understanding the same basic physics. Okay.
I'll tell you about 7 minutes.
Okay, 7 minutes, cool. All right, let's just keep pushing. Yeah. Let's go to vectors. Okay, let me try to do this a little faster than I would have liked.
Don't speed up so much that we don't understand.
Okay, I feel I'm kind of I'm slow right now, though, right? Like pretty slow, right?
This is good.
This is good. Okay, I'm seeing like this, and it's like just everyone will be angry at me, but that's cool. Yeah, it's fine. Yeah, it's good. It's good that people are angry. It means you're doing something wrong. So vector. Let's look at vector theories. Okay, things here are a little more complicated. Okay, now I haven't gotten to those really nice variables called spin and helicity yet. But we're going to have training wheels right now, okay? So what are our training wheels? Our training wheels are, we're going to use momenta. And we're going to use polarizations, okay? Now this has redundancy in it. This is not the way I would necessarily want to do this, but let's inch our way towards a bootstrap. The idea is I'm introducing these, but not with the preconception that it came from the Yang-Mills Lagrangian with the Lie algebra, this and that. Let me just assume that I'm trying to build a function that has momenta, polarizations, and of course, has to satisfy the Ward identities so that the unphysical polarizations decouple. Okay, you can think of that as a from on high constraint. Okay, so what are our inputs? So again, I have to say this: I squared equals 0. Okay, so is pi dot ei as usual, and let me even work in a helicity basis where ei squared is 0. Okay, I'm doing general dimensions. Okay. The idea is that we're going to bootstrap vectors, at least in some simple cases, in general D, using the same kind of idea. Okay. Now, if I just enumerated the kind of invariants, let's do that. Well, what are they? Well, we have E1, E2, we have E2, E3, E3, E1. Okay, these are just some simple Lorentz invariants, definitely present. And we just keep enumerating. Okay, so let me write down what's called a minimal kinematic basis. Explain what that means in a second. Okay. Okay.
And E is the same as epsilon?
Yes, sorry, I keep switching. Yeah, E is the same as epsilon. I apologize. I will always mess that up because that's kind of, those are like the same symbol somehow for me. Yeah. Okay. Now, yeah, sorry for that. So I haven't written down every Mandelstam you'd think you would have written. Okay. P1.P2 isn't here, but that's okay. We know that that's 0, so that's why I threw it out. You would have imagined there's other P.E's that I didn't write. Okay, but I eliminated them using on-shell equations. Okay, so I'm not going to do that explicit here, but let me just say it. Okay, anything involving P3, I can use momentum conservation to get rid of it. Right, as minus P1 minus P2. Okay, so if you like, you can eliminate by momentum conservation P3. Okay, that's why nothing here involves P3 because I used total momentum conservation. There's also no p squareds, as I mentioned. There's one other Mandelstam here that you might think is missing, which is p2.e3, or similar things. Okay, it's not in the set, which I'm calling my minimal kinematic basis. Okay, but the point here is that I can rewrite this as minus p1e3. Why is that? Because I can write p2 as minus p1 minus p3, and p3.e3 is 0. Okay, so if you like, I've kind of taken all the conditions that are fixing this to be on shell and used it to remove Mandelstams from my basis set. Now, if you don't do that, you will get inconsistent answers. Because if you tried freely moving all these around as independent objects, you'll leave the on-shell surface. You won't be talking about it at physical anything. Okay, so it's important to kind of reduce to this basis. Okay, that's the only trick we'll need, really, to bootstrap a fair amount of, well, some amount of gauge of what we know about how vectors interact. Okay, let me do this quickly. Okay, so let's build an ansatz. Okay, what's an ansatz look like for a vector? Okay, so we know that it should be multilinear in the polarization, so it should look like E1 mu1, E2 mu2. Sorry, little e1, little e2, little e3, mu3 times junk. Okay, so we just want to write a product of Mandelstam invariants that has one e1, one e2, and one e3. Okay, because we're doing a vector. Let's do that. Let's just write down the ansatz, and I'm going to do it more explicitly right here at the start, and then less explicitly as we do bigger, more interesting theories. But again, since this is the first pass, let me just do it fully. What is this A3? Okay, I'll leave this as an exercise so you see that this is the only object. And I'm gonna put free coefficients, right? We're doing an ansatz. So there's this free coefficients, I'll call C. C times E1, E3, P1, E2, C2, E1, E2, P1, E3, plus C3, E2, E3, times P2, E1. Okay, so this is the only object you can build out of these basis elements, which has 1E1, 1E2, 1E3 in each term. At order linear in P. Okay. As usual, we have to make an assumption about what momentum counting we're at. You might ask what happened to P to the 0. Well, with P to the 0, you wouldn't be able to contract the Lorentz indices correctly. We need an odd number of momenta because there's an odd number of polarizations. So the leading thing you could write is at order P to the 1. Okay. Good. Here's the ansatz. Okay. Let's sculpt out from this ansatz something interesting. Well, as I said, again, this is gauge symmetry, but this is the constraint we impose since we've decided to use polarizations. There's a Ward identity, which says that the unphysical polarizations when E1 goes to P1, when E2 goes to P2, and when E3 goes to P3, these are all 0. Okay? So it's the statement that the E mu has too many degrees of freedom inside it, so we have to make sure that some of those decouple. And this just gives us equations. Okay, so let me do parentheses squigglies because it's too much stuff to write. But this thing is proportional to C1 plus C2. This times kinematic stuff times some fixed kinematic function. This is C2 minus C3. This is C1 plus C3 times kinematic stuff. Okay, so there's like E's and P's in here. That doesn't matter. The point is that the set T is to 0. It fixes the couplings, the free parameters. Okay, and the solution is that C1, C2, and C3 are proportional to 1, minus 1, 1. Okay, and I'm just gonna minus 1. And I want to just say in words here that when you evaluate equations like this, you always have to keep going back to the minimal basis. If you ever leave the minimal basis, start saying things, you have an over-redundant set of variables. So any equations you write, you should write in that basis, and this tells you in that basis, you would find as an exercise this constraint which fixes all the coefficients uniquely up to an overall constant. Oh, okay, let me find, I just need 2 more minutes. Yeah, can I get 2 more minutes? Yeah, yeah, he's very angry at me, so let me finish with, I just need 1 minute for this. If you look at what this function is, you'll notice it's actually very familiar. Okay, it's you can write it as A3 equals E1 E2 times P1 E3. Sorry, E P2 E3 plus cyclic. Okay, the other 2 cyclic combinations, which you'll recognize precisely as the kinematic amplitude you get in Yang-Mills theory. Okay. But I haven't assumed anything about Yang-Mills theory yet. I've just built this function. Okay, so let's actually study it in this last 30 seconds I have. So look at this function and think about its isometries. And imagine there was only one vector, because that's what we started with. I didn't tell you about non-abelian anything, just one vector. This is like a photon. Okay? This object is antisymmetric in swapping 1 and 2. Right? If you swap 1 and 2, this is invariant, but you get a minus sign. So this thing is antisymmetric under swapping 1 and 2, but we're trying to just find a vector, which would be both symmetric. So what do we learn? This thing doesn't preserve spin statistics, so this is actually 0. There is no 3-particle amplitude of 3 vectors that are the same vector. Doesn't exist. And you know this from QED. There's no 3-photon vertex. It's excluded by Furry's theorem, yada, yada, yada. We have other kind of quantum field theoretic arguments for that. Now, how do you get around that? Well, you can't if it's one vector, but if you have multiple flavors of vectors, okay, then there is a coupling constant, which has a freedom of symmetry or antisymmetry. Let me call that F, okay? And I'm using that on purpose as the form of a structure constant. So in other words, let's say there's flavors or colors of vectors labeled by A1, A2, A3, okay? Then if F is antisymmetric in its indices and cyclic, then since this momentum piece is also antisymmetric and cyclic, then the whole thing is actually Bose invariant. Okay, so what we learn is that the only way to salvage this thing is to derive the Yang-Mills three-particle amplitude. Okay, so okay, I wanted to say more, and I will just, I guess, continue later. But the point here is this structure constant didn't get input through some Lie algebra. Like, if you notice, it's just a thing that had to exist for this to be non-zero. Later on, we're going to derive the rest of that structure, the Jacobi identities, all those, again, in this oblique way. Okay. Before that, we'll look at more derivatives and gravity, but maybe this is a good place for me to stop.
One quick question before coffee? Yeah.
Yes, indeed. So for multi-flavor, okay, what's the rule? So if I had, so the question I should repeat was, if there are more than one scalar, how do you do this bootstrap? Well, the idea is, in addition to the kinematics, there's also a coupling constant, like lambda, ijkl. Okay? And you just have freedom now. Like, if you want to make lambda ijkl fully symmetric, then everything here should be fully symmetric. But if you wanted this to be, let's say, I don't know, anti-symmetric in the first two indices, anti-symmetric in the second two, but symmetric under swapping the pairs, for whatever reason, then you get other isometry properties. And you can just assume what you like. So indeed, this kind of bootstrap works. Permutation invariance was just a nice output of a single scalar. But for any choice you make, you'll bootstrap it. There's no magic. Yeah. Does that answer your question? Yeah.
All right, great. Well, let's have some coffee. Let's thank Cliff again.
Yes, absolutely. Yeah.
I think it was not clear for me, like, all these bootstrap things.
I'm getting a high five. That's a good high five?
Yeah.
Good high five. Okay, cool.
Can I take your mic as well?
Yes. Yeah. So we're not publicly. I can finally impugn my colleagues. Good. Yeah. Yeah.
Sorry. Discharge it. Yep. Thank you.
They are like all three.